Yeah, I think it was the last recording. What had happened was the microphone cut out halfway through, so I just tagged one from last year. But looks like everything's working now, so let's cross our fingers. Okay, attendance grades are up to date. I called the ball and said we're not going to have class on Friday. Okay, we have green and white day on Friday. I really wanted to do that lecture in person, but I can't. So I pre-recorded it. It's already recorded and ready. I might show you a couple things with that lecture today, just because there's some really nifty stuff with it. But today, what we're going to do is sort of continue our construction of influence lines. Now, we're going to handle two types of problems today that are, again, the first one is, again, quirky. The second one is a lot more straightforward, but it is a little bit more brute force, and that's how to handle influence lines for trusses. The short answer is that the Mueller-Breslau principle works in theory for trusses. In application, it doesn't, because you have to take a truss, remove a member, displace that member, and then see what the truss looks like. And I don't know anybody that can do that in their head. So the only way to assess it is to just like brute force the influence line. And you'll see what I mean here in a little bit. Okay, bless you. Now, today's lecture, and particularly looking at influence lines for fixed supports, really turns me into a lawyer, I guess, when it comes to reading the definitions for an influence line and the rules that we use, because you have to apply them very expeditiously to get the influence lines for dealing with fixed supports correct. And they're actually easy if you understand the rules, okay? Now let's just make sure we're clear on the Mueller-Breslau principle again. So again, what we're doing is we're saying that if we take a structure and we identify a response of interest, a reaction, a shear in moment at a given point, whatever, in any force response of interest, we take that structure and we remove from it the ability to resist that response and move it through a unit displacement. Whatever the structure looks like after the deformation, that is a scaled representation of the influence line. Now, the issue, though, is we have to make sure that we are crystal clear that what we have been dealing with this whole time are statically determinate structures, okay? And what I mean by that is when we take a statically determinate structure and we remove from that structure the ability to resist a given force response, we turn it into an unstable structure. And unstable structures don't flex, they don't bend, okay? So when you're dealing with fixed supports, you got to be careful on how you construct the influence line, because I can't tell you how many times I've seen an exam or a homework assignment and the rules are the rules, but then when I look at the influence line, they're curved because the rules weren't fully employed, and then you're looking there like, I don't know how to draw the influence line, so I'm just going to make it curved, and that's wrong, okay? Now, I want to be clear, okay? None of those rules that we developed are invalid for fixed supports. Okay, you just got to be careful with what you're doing. Okay, let's consider the influence line for the vertical reaction at a fixed support. Okay, now everybody watch this. Okay, so we take the structure, we remove from the structure the ability to resist the vertical reaction. Okay, we'll say it again. Okay, we're drawing the influence line for the vertical reaction. We remove from the structure the ability to resist the vertical reaction. And we move it through a vertical translation. But what we didn't do is remove from the structure the ability to resist rotation, okay? We didn't remove that moment reaction. So if we were to do that, that's wrong, okay? That's wrong, okay? Because over there on the left, not only have we translated it, we have rotated that point as well. What the correct thing would be to do is to do that, to take the whole thing and just pick it up. Okay? I'm going to show you why in an example today, but the point I'm making is that whenever you're dealing with a fixed support and you have a vertical reaction, you do not rotate the point, you just translate it. Okay? And like I said, here in a second you'll see the statics of why that works. Okay? But I can't tell you how many times I've been looking at exam problems and whatnot, and I see students do this, okay? They do this, and then what happens is when you get later on into a deeper part of the influence line, what they've got doesn't make sense, and so they're having to curve the influence line to get it to connect, and then it's wrong, okay? So, that's wrong. That's right, okay? And similarly, on the flip side, if I wanted to draw the influence line for a moment reaction, I would rotate the support, but I wouldn't translate it, okay? So it wouldn't move up and down if I was drawing the influence line for the moment at A, it would just rotate, okay? And to explain what's going on here, I kind of want to look at this problem, okay? So for this problem, this is just as simple as it could be, cantilever beam. And I want to draw the influence line for the vertical reaction at A, I want to draw the influence line for the moment reaction at A, and I want to draw the influence line for the internal shear and moment at B, okay? Now, before we start drawing the influence lines, okay, I want to consider the statics of the situation first, okay? In other words, remember the Mueller-Breslau principle, this graphical approach of removing responses and moving the structure through a displacement is a shortcut, okay? Really, the brute force approach is just taking the load and moving it across the structure and recording the response. Moving it and recording the response. Moving it and recording the response. Just a statics problem, okay? Now, let's take a look at this. Consider the following, okay? So I have a beam and I have a point load on the beam, okay? Let's call it 1 kip, all right? And let's just put it some distance x away from the support, okay? Now, if I look at this from a statics perspective, so I have a vertical reaction AY and a moment reaction MA. Help me out. Summing forces in the Y direction, what is AY? Say it again. 1. It's 1 acting upwards. Now you gave a very interesting answer because what you're telling me is this. Where is that load along the span? Did I tell you where it was? No, it's X. Like X is variable, right? But what he's telling me is that it doesn't matter where the load is along the span, the vertical reaction is 1, right? If I take a 1 kip load on this beam and I put it here, the vertical reaction is 1. Put it here, vertical reaction is 1. Everywhere along the beam, the vertical reaction is 1. I propose to you that the influence line for the vertical reaction at A is just this. Now, does that comport with the Mueller-Breslau principle? Well, hold on. What does the Mueller-Breslau principle state? We remove from the structure the ability to resist the vertical reaction at A, and we move it through a unit translation. But we do not rotate it. We do not rotate it because it's a fixed support, okay? So how do we take point A, and lift it up such that it doesn't rotate? I don't do this, right? Because doing this not only translates it, but rotates it as well. I have to take the whole thing and pick it up. That is the influence line for the reaction today. It's just a constant 1. Does that make sense? With me so far? Now what about, let's go back down here. Now let's look at the moments, okay? So for the moments, let's do this. So, here I'll sort of isolate this so we all know what we're looking at. So I've got, what do I have? I have MA acting like this, and I've got 1 times X acting like that. So X equals MA. We've got MA equals X and AY equals 1. That's interesting. If I were to graph y equals x, what does that look like? It's just a line, right? It's a line with a slope of equal to 1, right? I propose that the influence line for the moment reaction at A looks like that. Now, does that comport with the Mueller-Breslau principle? Well, hold on. I take the structure and I remove from the structure the ability to resist the moment reaction at A. I then take that reaction or that point, and I move it through a unit rotation. Now, hold on. Let's break that down. Unit rotation. What does a unit rotation mean? The unit rotation means that the slope of that line is 1. And if the slope of that line is 1, and I go over 20, I go up 20. Now, one thing that is customary to do when you're drawing influence lines for moments is usually what I like to do is I like to put my sign for moment reactions just to make sure that it's clear that, you know, I'm drawing that moment reaction in alignment with the sign convention I've established. I don't think that's all that necessary for influence lines for vertical reactions. I mean, if I want, I could say, you know, this is, you know, positive upward, but I mean, I think that's pretty clear that positive reactions are going to be upwards, so I don't really think we need to worry about it. All right, before we go on to the internal shear and the internal moment, let's take a step back and let's see if this makes any sense. Is everybody okay with this? So far, so good? So, like, for example, to give you some, like, wonky example off to the side here, we'll do a little side calculation here. Right? Let's do something, like, stupid. Right? So if we had, let's say, this, and this, and then we had a hinge, and a hinge, right? So that is a statically determinate structure, right? Okay? And we removed from the structure, let's say, the ability to resist the vertical reaction right here, and we're drawing, let's call that AY, and we're drawing the influence line for AY. What we're doing is we're taking that point and moving it through a, let's say, unit translation, but not a unit rotation. So what that means is that stays straight. right? And then we're going to go through there, go like that. Here, let's. Man, my scale is. Let me redo this a little bit. Let's redo the scale a little bit. Right? So what do? We go here, the hinge changes the direction, 0 through the support, hinge changes the direction, 0 through the support, hinge changes the direction. So that would be what the influence line for AY would look like. Does that make sense? And actually, hold on, that's going to bug me if I don't make that flat. That needs to be flat. I'm not sure that that's a whole lot better. But to be clear, this follows the same rules that we had discussed before. 1 here, 0 here, 0 here, 0 here, 0 at the other supports, right? The hinge changes the direction. It's a series of solid lines, right? So that's the influence line for the reaction at A in a beam like this. Does that make sense? That's a crazy one, but I mean, it's not hard, you know. All right, let me stop for a sec, see if anybody has any questions. Okay. All right, so now let's go back to the other part in the problem. The other part of the problem said, okay, influence lines for internal B and M at B. So here's the beam. Okay, and in this case, point B was right there. Point B is right here. Why is it not changing color? Okay, that's point B right there. This is point A, this is point C. Okay, so do this. That's enough. Let's start off with the shear. Okay, so we're going to draw the internal influence line for the shear at B. Okay, now, how does this work? Okay, so what we do is we say, okay, I'm going to install a shear release there at B. Okay, so I remove from the structure the ability to resist the shear at B, and then I move that structure or that point through a unit displacement. Okay. Before we start drawing this, let's write some stuff out. Rules for shear influence lines. When I move it through a unit displacement, before what we would do is we would move the left side down, the right side up a little bit. How much was that total jump? 1. Total jump. Total jump is 1. Now, we didn't just willy-nilly do that jump. We did it a certain way. Like we moved the left side down and the right side up. But how did we figure out how much we did? Like how did we do that? What was the key fact that we had to maintain when we displaced the left side down and the right side up? What was it?
1 Is H2 equals 1?
What, the total height's 1, but like that, so we knew that the total height is 1, but what was the other fact that we knew about these two lines?
The slopes.
The slopes were the same, right? So we knew that we had equal slopes on either side of the shear release. We knew we had equal slopes on either side, okay? All right, now here's the new fact, okay? This is the structure, okay? I have installed a shear release at B. Did I do anything at all to support A for this? Have I done anything to it? No, okay? So fact 3 for this beam, since A is still fixed, it can't translate or rotate. Therefore, slope and deflection at A is 0. So how do I adhere to all of these rules and draw the influence line? How do I draw an influence line with a total jump of 1, all right? Equal slopes on either side of the shear release, and point A can't translate or rotate. Here's how you do it. That is the influence line for the shear at B. That's your influence line right there. Now the left side tends down, the right side tends up. It just happened that the right side jumped up to full 1 and the left side tended down to full 0. Does this comport with the statics? Well, let's take a look at it. Okay? Let's take a look at whether or not this comports with the statics side of things. Let's see. Okay, I want to look at two cases. Here's the beam. Here's the beam. Okay? Here's the beam, here's the beam. My point of interest is right there and right there. Okay? Now I'm going to look at two different load cases. The first load case I'm going to have is the load over here. And the second load case is what about the load over there? Okay? What happens if I samurai sword or lightsaber through these beams at my point of interest? Call that section 1-1. What about over here on the left? Just look at the structure. Ignore all the influence line stuff. If I told you to cut a section, what would be the easiest way to look for this? Because remember, we got reactions over here. You know, we got, don't forget, we've got an AY, an MA, an AY, an MA. What's the easiest way to look if I cut a section?
Right.
Right. And so if I cut a section and look to the right, what do I have? I've got this. There's my section cut. And I have positive shear, positive moment. There's my free body diagram. What's the shear? It's 0, right? What about over here? What happens if I cut a section? I've got my load to consider. Here's my section cut. Here's my shear. Here's my moment. Drawn according to positive sign conventions. Any time that the load, this 1 kip load, anytime it's over here, the shear is 0. Anytime the load is over here, what's the shear? I got 1 down, 1 up. So what's the influence line look like? 0 over here, 1 over there. That's the influence line for the internal shear at point B. Does that make sense? Like I said, quirky. Let me stop for a sec. I want to see if anybody has any questions on this. This is kind of important. This is probably the trickiest thing, by the way, between now and the end of the class, is this. Does that make sense? What about for moment? Okay? What about for moment? Watch this. Moment's pretty easy. Okay? Moment, we have a beam, and now what we're going to do is we're going to install a hinge at our point in question, right? That's our point in question. This is A, B, C. Okay? Right? This is 10 feet, 10 feet. Right? So here's our guidelines. We draw our influence line for the moment at B using very similar rules. Okay? What do? We insert a hinge at point B and we move it through a unit rotation. Okay? But again, with the shear influence line, I didn't do anything to this support right here at A. So how do I rotate point B with a slope of 1 without doing anything to point A? Simple. My influence line looks like that. That's the influence line for the internal moment at B. Okay? And how do I figure out this value right there? Well, the slope is 1. I'm going to call it -1 in this case. The reason I'm calling it -1 is because if I've got my beam and I bend it, it tends to do frowny face bending, so that's why I'm drawing it negative for internal moment. So if this has a slope of 1 and that's a length of 10, that value is -10. Notice how, again, that also comports with these free body diagrams up here. If I have a load that's placed before my section of interest, and I cut a section to look to the right, there's nothing there. Anytime the load is over here, it has no effect on either the shear at B or the moment at B. But the further that load gets away from that section cut, it's going to cause more internal moment, and it causes it at a linear relationship, just like we found with the moment reaction. That is your moment influence line for the internal moment B. What do you think? Any questions? Did I blow your minds a little bit? All right. I want to show you a couple things real quick, make sure we're not running out of time, but I want to show you a couple things real quick. Okay? You don't need to write all this down. I'm not making you redo all this, but I kind of want to make a point on something. So, first off, I want to talk about influence lines for trusses, okay? The Mueller-Breslau principle for trusses, like the theory works, but the drawing, using the Mueller-Breslau principle for drawing the influence line doesn't really work well in practice. There are actually ways that you can make a software to do it. One of the things you can do is actually model a truss and then take one member and heat it up or cool it down. But usually what you would do is heat it up and move it through a unit translation and then see what the truss looks like afterwards. So all I'll say is that it works in concept, but it's very difficult to apply practically. Really, the only way to draw an influence line for a truss is to do it through brute force. In other words, take the truss, move the load, analyze the truss. Move the load, analyze the truss. Move the load, analyze the truss. Now we can still use the Mueller-Breslau principle for the support reactions. That one's easy. And you'll see what I mean here in a second. Now, one of the questions that you'll have to answer as you're doing an influence line analysis is the load applied at the top of the truss or is it applied at the bottom of the truss? Because remember, the load moves across the structure. And my answer to that is apply the loads where the road would be, okay? So for example, if we're talking about this structure here, what happened there? If we're talking about this structure over here on the left, so what we would do is we would move the loads across the structure. So I would put a load at this joint, analyze the truss. Then put a load at this joint, analyze the truss. Then put a load at this joint, analyze the truss. And I would move it across the bottom of the structure because that's where the road is. Because keep in mind, we're talking about assessing a structure subjected to loads that move. We're talking essentially about bridge engineering applications. So put the loads where the trucks are going to be. Whereas with this truss right here, what I would do is I would move the loads across the top of the truss. I'd put it right there, analyze the truss. Then right there, analyze the truss. Then right there, analyze the truss, etc. Does that make sense? There's no real point in moving a load across the bottom of the truss because there's no cars down there, okay? So that's really sort of the logic. Just apply the load on the path where the road is, okay? Make sense? Now, let me show you how this works. And again, you all don't really need to write this down because I'm not going to make you do this. I'll just point blank tell you, I'm not going to make you do this on an exam because this just takes too long, okay? But I do want you to kind of understand how it would work, okay? So let's say I give you a truss and I say I want you to draw the influence lines for some members, okay? So let's say member AB, member CD, and member CH, okay? So the way that this would work is, okay, let's say the road here is along the bottom of the structure, okay? So what I would do is I would place a load at B, and then I would analyze the truss. Okay, then place the load at C, and then do the truss analysis all over again. Do it again. Then place the load at D, do the truss analysis all over again, right? That would just be an absolute ridiculous pain, okay? So instead, like if I was doing this on, let's say, a homework assignment or even as a practicing engineer, honestly what I would do is I would say, I'm not doing this by hand. Let's let a software program do it for me. Okay, so here's that bridge. I went ahead and modeled it. Okay, so what I would do is I would say, okay, conditions, forces, let's apply a -1 force at node 2, apply, and then analyze it. Wait, what did I do? Oh, wrong. And then analyze it, okay? And so now what I would have is I would have, let's say, okay, I placed the load at, we'll call it joint B, joint C, joint D. I'm not going to place it at the beginning or the end because I know if I place a load directly over the support, the truss isn't going to see anything, right? So what I'll do is I'll say, okay, let's start recording member responsive interest. Let's look at like this member right here, okay? This member is member AB, just as an example, okay? So now that I've analyzed it, what I'll do is I'll say, okay, let's go to results, element forces, and let's pick this element right here. So when I analyze it, I'm getting a value of 1. Okay, so I put a 1 tip load there. That's what I get. I get 1. Now what I'm going to do is I'm going to Now hit cancel. I'm going to go to conditions forces. I'm gonna clear all the loads off the structure. Now what I'm gonna do is conditions forces, place the load right there. Now put it in the middle joint, analyze it again. Analyze it, now that's done, results, element forces. Now let's go to that same member, and now the element force is 0.6667, okay? So we'll say that here, 0.6667. So what do you think that was going to be? I'm just curious. Keep in mind these are influence lines. What do you think that's going to be? This is 1 and this is 2/3. Let's see if I'm right. So conditions, define forces. Now let's put -1 load there, apply, analyze structure, results, element forces. Let's look at our member again. And by golly gosh gee, I know it's kind of hard to see, but 1/3. So if I wanted to draw, if I go back here and I wanted to draw the influence line, let's say for member AB, so the influence line for member AB, okay, what it's going to see is this is 0, that's 1, and then that's 2/3, 1/3, 0. That's how it's done, okay? Instead of me going through and solving every member across the structure, that's how you would do it, okay? Does that make sense? So one thing I'll tell you just in general, okay, when you're doing influence lines for trusses, okay, because this is actually kind of a popular question on the FE exam. So if you're looking at this truss, so what I'll say is members on the bottom tend to have influence lines that kind of look something like this, because as you apply a vertical load across the structure, the bottom of the truss is experiencing tension. So all the members are going to have positive influence lines, okay? Members on the top on the flip side, so if we were to draw the influence line for like member FG, what would happen is it would probably look something like that. Because if I put think about it, a truss is just a really big beam with holes in it, okay? So if I'm loading the beam, the top's experiencing compression, the bottom's experiencing tension, right? So the influence lines for the members on the top are all going to be negative, okay? Now the interesting thing is that if you look at the inner diagonal members, what happens with the inner diagonal members is this. So we'll say interstitial diagonals. What happens with them is they kind of like will do something like this. They'll go down and then they'll jump and come back up. And the reason for that is, so the best way of describing it, if the top and bottom chords are what are sort of carrying your quote unquote moment, then the interstitial diagonals are sort of carrying your quote unquote shear. So they're going to like flip direction, just like a shear influence line would. Now, dependent upon whether they start down and go up or they start up and go down, it just depends on which way your diagonals face. It's like, for example, if you take the diagonals and flip it, it'll take your influence line and flip it. And honestly, the best way of figuring this out is to just take this truss and go through a few of these and see what they look like. So, again, I'm not going to make you do that on an exam. I just kind of wanted to go through that with you all in here. Does that make sense? All right. Since we've got a few more minutes, I kind of want to show you some of these applications because I think this is really cool stuff. Does anybody have any questions about this so far? Okay. I'm gonna steal my own thunder a little bit in this recording I made, but I really think this is some cool stuff. Okay, so let me go to my next lecture. This is the one that I pre-recorded, but this is just some awesome stuff. Okay, so I want to show you some of the direct applications of influence lines, because the way, here's the thing, like, we've spent the past 3 lectures drawing influence lines, and I'm sure some of you are like, great, Dr. Mike, who cares? What the hell are we drawing these hinges and shear releases for? What is the value? What is the real value? Okay, there are 2 primary applications, and I kind of want to walk through the first one with you together, because this is nuts how this works. Okay, the first application, I would say, of an influence line is to replace equations of equilibrium and to just do the structural analysis directly. Okay, so for example, what is an influence line? It is a plot that shows you the effect of a moving unit load. Well, if I know the response due to a unit load, why can't I find the response due to any load? Okay, and particularly I'm talking about vertical, concentrated, and distributed forces. So how would I do this problem? How would I analyze this problem right here? Okay, well, the way I would handle that is I would say, let's just take the concentrated forces, multiply them times their associated values on the influence lines, take the distributed loads, multiply them by the associated area under the influence line, add all that up, and then now I have my response of interest due to the loads that are actually on the structure. Okay, and the way I kind of want to show you that is I want to look at this example. Okay, this is the one I kind of want to look at with you all together. Now, I've already done this example, so I'm not asking you to like totally repeat it here with me together, but I kind of want to walk you through this because this is just absolutely nuts. I go through this in much more detail in the next recording, but let me show you something. This is just crazy, so I think it is. Okay, so let me show you something. Let's see if I can zoom in a little bit. All right, so check this out. All right, so let's say I ask you to use the influence line properties to determine the support reaction over here at D. Okay, now let's just ignore influence lines for a second. If I gave you this problem and I said, how do you determine the reaction at D? This is how you would do it over here, okay? You would sum moments a day. So what does it look like when you sum moments a day? Let's take a look at that. Okay, so let's sum moments a day. All right, so how do I handle that? Okay, sum moments a day. I've got this load, 1.3 kips per foot over 20 feet. That's 26 kips at a moment arm of 10 feet, right? So I have that. 25 times 40, so I'm summing moments a day, so 25 times 40, and then 42 times 60. 42 times 60. That has to be resisted by a moment arm, dy times 80, right? So that times that is 260, that times that is 1,000, that times that is 2520. Sum that up, dy 80, divide. You believe me on that. Okay? Now, take that, ignore it. Now let's look at influence lines. I'm asking you to find the support reaction at D using the theory of influence lines. So let's draw the influence line for the reaction at D. So I pick D up. Would you agree that's the influence line? Okay? Now, look at the beam. The beam's 80 foot long. This is 20, 20, 20, and 20. So that's 0, a quarter, half, 3/4, 1, right? So watch this. 25 times a half, 42 times 0.75, 1.3 times that area. Sum them up, you get 47.25 kips. It's crazy, isn't it? Right? That's some pretty cool stuff, isn't it? When I first saw it, I was like, you gotta be kidding me. You know, that's crazy how that works. But the idea is that we can draw an influence line for a response of interest, right here, this dy, and now I can tell you what dy is due to any load anywhere without worrying about this stuff. All I need to do is just find the value on the influence line, multiply the area under the influence line for the load in question. So for the distributed load, I'm only taking that red shaded area because that's where the load is, right? So 0.5 times the base times the height is 2.5. So in order to determine this reaction, just 1.3 times that, 25 times that, 42 times that. Sum them up, you get the exact same answer. It's crazy, isn't it? So what we then do is we start in the next lecture is we start saying, okay, how do you determine the worst case response due to any load that you could place anywhere, okay? And I will tell you, it's a lot easier than you would think, okay? Because we're gonna have dead loads and live loads, and we have to place them in order to determine worst case response. It's a lot easier than you would think. Without influence lines, it would be an inordinately challenging problem. And with influence lines, we knock it out in a couple minutes. Cool stuff? I'm gonna pull up the QR code again, but that's all I got, everybody. I will see you all, hey, on Monday. Now, hold on, actually, I did think of one thing real quick. Remember, okay, I wanna make sure that this is clear on the announcements. So you have a homework today that's due Friday, and another one that I am assigning Friday that's due Monday, okay? So you do need to watch that lecture. I go through this problem in a little bit more detail, as well as some other application stuff. So make sure that you watch that. That's all I got. See you on Monday.